All right. So up first, you should have your 1B.6 polynomial functions in behavior part A. Okay. So for part A, we're going to talk about what is a polynomial function, right? We've already discussed before that by knowing the degree of the polynomial function, we can predict the end behavior, correct? Remember our little dancing Bob? So by using the leading term coefficient, the polynomial function, we can determine whether it's what the extremes are happening, okay? So just reiterating our rules. So if I have an odd positive, so a positive, I don't know why it keeps disconnecting my pen. There we go. If I have a positive odd, so a positive leading coefficient, but an odd degree, how am I behaving? What kind of dance moves are happening? Yes, remember we're staying alive, right? So if I have positive odd behaviors, we are staying alive. So we would start negative, but we're going to end positively, right? Ringing bells? Yeah. Staying alive? Okay. And then if I have a negative odd, I'm still staying alive, but this time my left hand goes up and my right hand is going down. Yes? Okay, so positive leading coefficient, odd degree. Negative leading coefficient, odd degree. Okay, we've already talked about how with even, if I have a positive leading coefficient and an even degree, we're going to be partying like we just don't care. We wave our hands in the air. Bob was doing this. Woo! Right? Yes. Remember Bob? Okay. And then if it's negative and even, so a negative leading coefficient, but an even degree, right, Jacob? Mm-hmm. We're just move our hands side by side. We're low-key dancers. We're like, not really doing a whole lot, just chilling. Okay. All right. So these are things that we already know. All we're going to do is focus on the terminology to explain those things. Make sense? Because we can't really say Bob is dancing. We can't say Bob is staying alive. All right. We can't say Bob is ready to go. Okay. Those are things we cannot say. Those are just ways to help remember. So we're going to focus on the terms that go along with it. All right. So when we look here, you will hear these phrases when describing in behavior a function. So it says, phrase 1, the input increases without bound. Okay, when I'm saying the input increases without bound, that means as x is going to positive infinity. So translation, the x values are moving towards infinity. Okay. Now, if I said the inputs decrease without bound, what does that tell you x is doing? If I was increasing without bounds, and that meant x was going to infinity, what does that mean x is doing now? Going to negative infinity. So in words, that means the x values are moving towards negative infinity. Okay, a lot of times that is not that you guys don't know how to do things, it's the words that get you jumbled up. Does that make sense? So we want to make sure that the vocabulary isn't our downfall. All right. So with that same logic, the outputs increase without bound. I'm now saying output. So now I'm describing what? The y's. So our y is moving towards positive infinity. So that means that the y values are moving towards infinity. Okay. And then the outputs decrease without bounds. That means our y values are going towards negative infinity. So the y values are moving towards negative infinity. Okay. So more than likely, as you evolve in math and the test goes, you would see it says describe what's happening as the input increases without bound. It's just simply asking you, what are your x values doing as they go forever to the right? Does that make sense? What are your x values doing as they go forever to the left? Would be decreasing without bound. Okay. Without bounds just means what are your extreme situations taking place? Got it? Because if we don't give people boundaries, don't some people take it to the extreme? Yes, they do. All right. So that was thing number one, is just clarifying vocabulary in terms that may appear. Got it? All right. Next, we're going to talk about visualizing the language. So when we're talking about visualizing, that's just reiterating what I just said, the direction that we're heading in. Okay. So your X's are either going right or left, and your Y's are either going up or down, correct? So here it says, if the inputs increase without bound, what direction am I heading? Logically, we're heading to the right. If the input is decreasing without bound, what direction am I heading on the graph? To the left. If your output is increasing without bound, what direction is it heading? Up. And if your output is decreasing without bound, what direction is it heading? Perfect. Okay. So what I would like for you to do is you're going to create your own little polynomial, and then you're going to have your neighbor describe the end behavior. So in that box, you're going to create your own polynomial, and your neighbor is going to describe the end behavior to you. All right. If you don't have a neighbor, then find a neighbor. But you're going to describe what's happening. You can be as creative as you like with but you're going to describe what are my end behaviors taking place. All right, go. I don't hear y'all talking. So draw and then partner up and describe what's taking place. You're drawing your own and then having your neighbor describe your end behavior. Okay. Any polynomial, whatever the spirit tells you to draw is what you draw. We're supposed to be practicing using our vocabulary, right? So I'm just going to draw a quick little easy peasy one. Okay, so when I'm using the vocabulary, I'm going to describe what's happening to the right. So I would say, as the inputs increase without bound, my output is doing what on the right? My output is increasing without bound. Do you see that? As my input decreases without bound, which means I'm going to the left, what is my output doing? My output is decreasing without bound. Agreed? Yeah? Okay. So that's how the terms are used. That's all you're doing. It's saying what's happening as you go left, right, up, and down, and corresponding without bound. Yes? All right. Are we feeling okay with the terms? Perfect. Okay, so we're going to continue. Are we on the back, right? Okay, flipping over. So putting it all together, the end behavior function describes what the values are doing. So what your y values are doing of a function are doing as the x values are either increasing or decreasing without bound. Hence means that we're heading towards either positive or negative infinity, right? Yes. Without bound just means describe positive and negative infinity. Yes. All right. Your left end behavior of a function describes the output values of functions are doing as the input values decrease. So as your input decreases, we call that our left end behavior. Okay. This is what we call the limit of the graph, which we're leading into. Okay, your right-in behavior of your function describes what the output values of the function are doing as the input values are increase without bound. And that would be called our right-hand limit. So that's the limit. So we're building up to the word limit. Okay, so double checking that we understand what's taking place. In words, you're going to describe what happened. Limit. In words, you're going to describe this function. Hint, we just did it. Mess it up and write the wrong words. I am going to blame you. It's not going to be me. We just modeled it out loud, remember? All right, so in words, describe what's happening to my outputs on 1 and 2. So write it out. Looking at this function, this is our g of x. Using our vocabulary, what is taking place? August. As the input values increase without bound, what are the output values doing? Increasing without bound. Good job. No. All right. Emiliano, as the input values decrease without bound, what are the output values doing? Perfect. We are decreasing. Okay. So when I'm looking at as my input values are increasing, remember that means I'm going to the right. When I'm looking at when my end values are decreasing, that means I'm going to the left. Okay. I know it sounds repetitive, but a lot of time for vocabulary and unfamiliar phrases, we have to hear it over and over for it to click. Make sense? So this leads us to describing what's called a limit. So writing in limit notation. So verbally, we are saying as x approaches infinity, positive or negative, our f of x approaches ... right? Approaches negative, positive infinity. Symbolically, we're going to be using as x goes to infinity or negative infinity, what is your f of x doing? And this is our end game right here. Our end game is to be able to write it in limit notation. So our limit as x goes towards positive infinity, f of x equals this or that. Our limit as x goes towards negative infinity, f of x equals this or that. Do you remember writing this in Algebra 2? On Bob, when we were describing his end behaviors, we were putting the positive or negative infinities as our limits. Bringing some bills. You do remember? We did, I promise. Okay. So let's fill it in. So our goal is to be able to write it as a left-hand and right-hand limit. So as x goes, so if I'm looking at the left-hand limit, that means my x's are heading towards what? X is heading towards negative infinity. As x goes towards negative infinity, as it's going, if I'm looking at left-hand limitation, left-hand limit, left-hand behavior, that means my x is going towards negative infinity. And then it's asking, what is g of x doing? What are your function doing? What is your y doing? Well, what is it doing? It's decreasing. It's heading towards negative infinity. So when we write this as a limit, our limit is the limit as x goes to negative infinity, g of x equals negative infinity. Because after a while, mathematicians got tired of writing, right? The x values are moving towards negative infinity without bound. They're like, how can we shorthand this, right? If I'm looking at the right end behavior, that means I'm describing when my x's are going towards positive infinity. If you want, you can always write the positive in front if that makes your heart happy. And as your x is going towards positive infinity, what is the y doing on this function? It's also going towards positive infinity. So my limit in this case would be the limit as x goes towards positive infinity, g of x equals positive infinity. Now, as we get into rational functions, are there going to actually be limits that we approach or try to approach? Yeah, because rational functions have special discontinuities. What are those called? Anyone remember? What are the discontinuities in rational functions called?
The ones that are like a line and then a line above it. Asymptotes.
Asymptotes. That's the word I was looking for. I was like, y'all just did your parent function project. Y'all should be able to tell me they're called asymptotes. Maybe it was the user. Maybe. All right.